Good evening, everyone.
Good evening. Good evening.
Good evening. So let's wait for 3 to 4 minutes and after that we will start. Okay, guys, we have waited enough. So once again, good evening, everyone. I welcome you all to the live session number 8 for the NPTEL course Hydrogen Energy Production, Storage, Transportation and Safety. The course instructor is Professor Pratibha Sharma from IIT Bombay and I am this course TA Amit Kumar Sharma. So today we are in our live session number 8. So the purpose of this session is to give you a rough idea about the assignment questions, like previous year's assignment questions. So we go through those questions and concept behind those questions. So you can revise the concept of the previous class and you can have like a knowledge of how to solve these questions. So the meeting is being recorded and the PPT and the recording will be shared to you from the NPTEL team. So let's start with today's class. So as of now, this is the course outline. So We have covered the production status. Now we are in storage. Okay. So question number 1 is how much amount of energy is released for conversion of normal hydrogen to equilibrium hydrogen? 572 kilojoule per kg, 620 kilojoule per kg, 307 kilojoule per kg, 527 kilojoule per kg. Okay, am I audible?
Yes.
Yes, yes.
Okay, and my PPT is visible to you?
Yeah, visible.
Okay, okay, thank you.
So
So
answer is 527 means D.
527. Okay, nice. So before live session, I always advise you to go through the last week's professor's videos so that it will be very helpful to you to participate in the discussion. Anybody else? Okay, we have an answer 5 to 7 kilojoule per kg. So your answer is correct. Nice. So now let's see more about this conversion. So first, I think we have already covered what are the two types of hydrogen?
Ortho hydrogen and
Oh,
para hydrogen.
Yeah, so we have covered previously also in our, I don't remember the week number, but we have also covered this in initial classes, I think week 1 or week 2. And in this week also, professor covered about the ortho and para hydrogen. So we have two types of hydrogen, ortho and para. What is the difference?
so parahydrogen is in the lower energy state. So in general, so orthohydrogen, when normal condition, that orthohydrogen will convert it to parahydrogen, and it will since energy content in orthohydrogen is more, so when it convert it to ortho to para, so some amount of energy will release. Means it is a it's a exothermic process.
Oh, nice. What about the spin? Why this ortho is in higher energy state and para is in low energy state?
Ortho is parallel and para is
इमिग्रेशन के लिए अगर इमिग्रेशन के लिए हम अपने बॉर्डर्स को
Yeah, please again.
ortho is parallel and para is anti-parallel.
Yeah. So the spin of nucleus is on ortho is parallel and para is anti-parallel. And what about the at room temperature? What about the concentration of ortho and para hydrogen in hydrogen?
85% ortho and 15% para.
No, I think seven. Uh, it is
I think it's 75, 25. 25 is para.
Yes. Yeah,
25.
75
Yes.
is ortho and 25 is para hydrogen. Okay. So the boiling point of hydrogen is very low boiling point 20 Kelvin. Okay. So to convert into the liquid, we need to convert the whole ortho hydrogen to para hydrogen. Ortho to para hydrogen is exothermic reaction. So what is the meaning of this?
Release the energy.
Yeah. So it will release the energy when you convert the ortho hydrogen to para hydrogen, because ortho hydrogen have high energy state. So when you convert it into para hydrogen, when you come to lower energy state, so the energy will be released. So it's an exothermic process. Important point, the inversion temperature of hydrogen is below ambient. Okay. Now what is the meaning of this inversion temperature and where we use this?
We use in for the Joule-Thomson effect, and this temperature is important. It decide based means how the temperature and pressure correlate.
Okay. So suppose if Joule-Thomson coefficient is negative, then what happens?
I think this inversion temperature, above the inversion temperature, there is heating on expansion for hydrogen per se, which is not the case for real gases. So liquefaction is difficult for hydrogen above this inversion temperature, which is 71 Kelvin. So you have to cool or compress and cool by other means and bring the temperature below 71 to enable the Joule-Thomson effect to be negative, and you can have cooling upon expansion.
Yes. So normally, if you are the inversion temperature is the temperature. If you are at the inversion temperature, then if you are doing the expansion, then there will be no change, no heating, no cooling. Okay. If you are above the inversion temperature, then what happens? Like suppose if your Joule-Thomson coefficient is positive, then what happens?
Cooling.
Yes. So the cooling will happen. And if the mu is negative, then heating will happen. So for the hydrogen at room temperature, the Joule-Thomson coefficient is negative. Okay. So it means that during the expansion, if you start from room temperature, so then there will be heating instead of cooling. So that's why you need to lower the temperature, because the inversion temperature of hydrogen is 71 Kelvin. Okay. So you need to come to this temperature. Is it 71 Kelvin, right or not? Am I right? Please check it.
Yeah, 71 Kelvin is the inversion temperature for
Yeah.
hydrogen.
Yeah. So below this temperature, when you do the expansion, then there will be cooling.
So can you please define inversion temperature, please?
So inversion temperature is like, you can say, the boundary. So at the inversion temperature, there will be no cooling or heating if you expand.
Okay.
Okay, so it's important property, in important, like you can say a temperature that is defined for Joule-Thomson coefficient, Joule-Thomson effect. So suppose if I remember the diagram correctly, so this is, I think, the temperature and pressure, and like this. So if you are moving at the so it's changing with the pressure also. So I don't remember exactly the, the access. You should check it. So the thing is that if you are at inversion temperature, then there will be no heating or no cooling. Okay.
Thank you. Thank you. Yeah.
Yeah.
Yeah, I think it's in the week 7, one of the lectures in week 7. This graph, yeah.
Yeah. So I think, yeah. In week 7, please go through those classes so you can know more about this. So now ortho to para conversion, because if we want to liquefy the hydrogen, then we need to convert the hydrogen to para. Okay. So ortho hydrogen, you can see they are having parallel spin, in para anti-parallel. So normally 75% is ortho hydrogen and 25% is para hydrogen. So at equilibrium you can see here 99.8% is para hydrogen at boiling point. Okay. So this is the curve. It's representing the para hydrogen concentration percentage versus temperature. So you can see. So if you are at 20 Kelvin at boiling point, so you can see it's almost 99.8. Okay. And if you are at room temperature, like here you can see it's 25% will be the para hydrogen and remaining will be the ortho hydrogen. The effect of pressure is negligible on equilibrium hydrogen, but of temperature substantial. The temperature is having, you can see here, large effect on the this change on the para hydrogen concentration. So complete conversion from ortho to para require 703 kilojoule per kg. Okay, the complete conversion from ortho to para. But from normal hydrogen, it requires 527 kilojoule per kg. So the question was how much amount of energy is released for conversion of normal hydrogen to equilibrium hydrogen. Okay. So it means normal hydrogen means there is how much will be ortho and how much will be para?
75%. Yeah.
75% is ortho. So you need to convert the 75% ortho hydrogen to para hydrogen. Then in this conversion, because it's exothermic process, so there will be release of 527 kilojoule per kg of energy. And the latent heat of vaporization is 446 kilojoule per kg. So stored liquid contains ortho hydrogen. There is issue of boil off. So what is the boil off issue?
Sir, before going to boil off, can you just, what is the difference between complete conversion of ortho to para 703 and from normal hydrogen? What is the difference in these two lines?
Yes. So yeah, the complete conversion from ortho to para. Oh, just a minute. I'm also okay. Okay, actually, I need to also check this.
See, because we have understood that liquefaction in the liquid state, ortho para is 99.8. So ortho is almost negligible.
Yeah.
So when you're saying complete conversion, I can understand that. But what do you mean by normal H2? That is what I was not understanding.
So I think
I think the normal H2 is where your ortho is predominant, right? The para conversion takes place only at lower temperatures. At normal room temperature, it is always ortho 99.5.
That is understandable. What I'm saying is, see, we have to convert the ortho to para to liquefy the hydrogen. That was the last session, right?
yeah.
So when you say complete conversion, you're anyway having a release of 703 kgs, which we all agree. But
Hmm.
what do you mean by
Yes.
from normal H2 is what I'm also not able to understand. Yeah.
So I think when we are talking about the normal H2, so it means that it is the combination of this ortho and para, 75% ortho and 25% para. Okay, so this combination you only need to convert the 75% of ortho hydrogen to para hydrogen when you say normal hydrogen. But when you say the complete conversion, it means that this case will considering 100% ortho hydrogen.
But we don't have any such state, no, sir. We have only, see, the normal state itself or a gaseous state, forget normal, gaseous state, you are having, I think you're right. I think you're right. It says the graph says 100%
Yes,
ortho,
yes. Yeah,
100% para. Okay, okay. Or maybe
Even
equilibrium. We have to understand the equilibrium hydrogen. That's when we'll understand probably.
even when we calculate 703, the 75% it comes to 527. I don't know. We can
yeah.
correlate in that sense.
So yeah, so this is the meaning actually from normal you're saying, then it means that the 75% is ortho and 25% is already para. Okay, the complete conversion means you are considering the whole ortho hydrogen.
Perfect. Okay, okay, okay.
Yeah, but
Thank you.
still I will see at what conditions there will be the full ortho hydrogen.
Yeah, that we have to find
Yeah,
out. And this
yeah, we have to find
equilibrium
out.
also, maybe I have to revise this subject.
Yeah, yeah. So I will check, and maybe in the next class I will let you know. Okay, so what are the conditions to have the fully 100% ortho hydrogen? Okay.
Thank you. Yeah, yeah.
Now this is an important term, boil off. What is this boil off?
So, uh, the boiling point of hydrogen is very low. So when you have release of energy from this conversion of ortho to para, some energy is used to might cause evaporation of the liquid hydrogen back into gaseous stage. That is called
Yes,
boil off, and it's a
that is
loss
called
term.
boil
Yeah.
off. Yeah, nice. So
It's
because
actually the heat loss term, actually, when you store at cryogenic temperatures. The
yeah,
heat seeps in and then it will lead to boil off of the liquid hydrogen to
yeah,
vaporize.
yeah, yeah. So correct. So as you know that this ortho to para conversion is exothermic. So there will be some heat release. So you are converting the ortho hydrogen to para hydrogen. Okay, and still the conversion is not complete. So some part is already in the liquid, some part is converting. But so there will be heat release. So due to that, some part of the liquid hydrogen will get the energy. Okay, and that will that because we know that for the liquid you need to temperature 20 Kelvin is the temperature. So due to the energy, the temperature will increase, and that portion will convert into the again gaseous state. So that will be the boil off. So the minimize evaporation in storage tank or through the para conversion is crucial, important for long-term storage. So it's very crucial actually. So when we want to store the hydrogen, then we need to minimize the evaporation or minimize the boil off losses in the storage tank. Okay. So liquefaction process have ortho to para conversion section to reduce boil off. So there are sections in this liquefaction process, so we can reduce the boil off. Yeah, so this is the inversion temperature and the pressure, the graph I was telling you in the last slide. So here you can see. So this boundary is showing the inversion temperature. Okay. This is the pressure. So here it's positive, I think the Joule-Thomson coefficient, and inside it negative. Okay. So the hydrogen liquefaction throttling is common to cycles. So after creating a known ideality condition, pressure increase, temperature decrease, or both, and the maximum hydrogen temperature is below the ambient temperature. So as we discussed already, for hydrogen, the inversion temperature is 71 Kelvin, and for helium also. For helium, I think it's around 50 or 51 Kelvin. Okay. So for helium also, when you do the throttling, there will be heating instead of cooling. So to have the effect of Joule-Thomson coefficient and to have the cooling effect, we need to pre-cool it. Pre-cool these gases, hydrogen and helium. We want to liquefy them. and also want to use the Joule-Thomson effect. Okay, so the pre-cooling is essential. So prior to 1895, so this was the process of liquefaction, compressing, then chilling, then expansion via throttling. So working media, hydrogen and saturated vapor, not returned as coolant after throttling. So after 1895, recuperative cooling employed. Liquefaction fluid act as a coolant. Thermodynamic effect used by the expanding adiabatically, either by mechanically extracting energy from fluid being expanded. Okay. Isentropic process by an expanding machine or without extracting energy. Isenthalpic process throttling. So this JT is a Joule-Thomson wall. What is the meaning of this throttling? Anybody wants to tell?
It is the sudden expansion in volume where you have the pressure increasing and
Increasing.
increasing. The throttling like
No, pressure,
Expansion is decreasing pressure.
pressure
Throttling
will
will
decrease.
decrease
so
the
you are
pressure.
saying
Yeah.
nozzle throttling is expansion, right?
Yeah.
So that means the I don't know the initial cross section is smaller, the end is higher, right?
You mean to
Like
say
if you
like
ask me,
this?
yeah. Oh, that is
No,
sorry. Then the
no,
pressure
it's
is
nozzle.
decreasing.
It's
Nozzle,
nozzle actually.
nozzling effect. Okay, I was thinking the opposite. Sorry.
Yeah. So anybody else?
Throttling is basically expansion through a valve,
Okay.
through an
So what?
orifice or a valve, or yeah.
Yeah. So what happens? Like, what is
It's
the?
constant enthalpy. I think constant enthalpy process.
Yeah. So what is the meaning of isenthalpic?
The inlet and outlet have the same enthalpies, but their pressure and temperature may change, but their enthalpy remains constant. That is, internal energy plus PV remains constant.
Yeah. Nice. Nice. So it's isenthalpic. Mean enthalpy
Yeah.
is same, but the pressure reduces. Okay.
Yeah.
Yeah. So expansion from P higher to P lower using Joule-Thomson wall, hydrogen partially liquefies, liquid collected and vaporefaction is allowed to exchange heat to cool hydrogen stream and then finally injected into the feed stream before compressor. So the cooling we can using two steps like pre-cooling and final cooling using recuperative. So next question. In which of the following cycle reciprocating expansion engine is used? Simple Claude cycle, dual pressure Claude cycle, Kapitza process, Lind-Hampson cycle. This is the direct question.
This is out of syllabus, I think, Amit. I've never heard this.
No, actually, yeah. If you have gone through the class videos, then yeah, it's direct
Okay.
question actually. The answer is C, Kapitza process. Okay, so these are the process by which we liquefy the hydrogen. Okay, so there are different kind of process. Some of these we will look into our upcoming slides. So for this question, the answer is Kapitza process. In this process, the reciprocating expansion engine is used. So the Kapitza process, use of reciprocating expansion engine, it is used for large scale hydrogen production is desired. Okay. Dual peak Claude process, minimum work for proportional to pressure ratio. Compression to energy varies logarithmic of compression ratio. So in ideal simple closed cycle, as the higher pressure, the minimum work of compression decreases, expander flow rate at minimum work decreases. About the capital cost. So for the capital cost of simple closed cycle is more than the Linde-Hampson cycle due to addition of expander and two heat exchangers. And the operational cost of cloud is lower than the Linde-Hampson and low power consumption is there. Which is the chemical method of hydrogen storage? Metal hydride, compressed hydrogen storage, cryo-compressed hydrogen storage, solid hydrogen storage. Temperature less than 14 Kelvin.
Metal hydride.
It's a metal hydride. Correct.
Okay. Yeah. The correct answer is A. Metal hydride. So this one is a chemical method of hydrogen storage. So there are two types of method: physical storage and chemical storage. In physical storage, the compressed state storage, liquid state, cryo compressed, and solid hydrogen. Temperature less than 14 Kelvin. Okay. Chemical storage have sorption materials, metal hydrides, complex hydride and chemical hydride, LOHC, and reformed fuels like ammonia, gasoline. Okay. Have you heard about the green ammonia? Anybody?
Yes. Means hydrogen may be generated from the green energy and that we are converted into ammonia.
Okay. So what is the purpose to convert to make green ammonia?
Actually, ammonia we can easily transfer from one place to another place. That's why it is a reliable method.
Green ammonia, is it?
Yeah.
So it is hydrogen comes from electrolysis for the Haber's process with nitrogen. Is it
Yes.
correct?
Yeah. Nice. So
Okay.
actually, if you are having the purpose of like green ammonia, because we have seen as of now that the hydrogen storage is difficult and also the transportation. Okay. In our previous class, if we have seen different types of storage like cylinders for hydrogen type 1, 2, 3, and 4. Okay. So the cost is increasing, also the density of hydrogen and all. So there are so many challenges in hydrogen storage and transportation. That's why it's easier to transport in the form of ammonia, NS3. Okay. And we know that hydrogen is a energy carrier. So you can convert the hydrogen into ammonia and you can transfer the ammonia. You can export the ammonia. Okay, that's called green ammonia. And then you again crack the ammonia to have your hydrogen. This is one use, like for the transportation, for the easy handling, to lower the complexity. Okay. And there is also another use. Suppose, because nowadays, like now it's okay that you are converting into ammonia, but the other main advantage is also that if you are having renewable energy. Okay. So your solar PV is working, your wind, you are having wind energy, so you are having surplus electricity. So if you have surplus electricity and your demand of hydrogen is not that much, then what should you do? You should convert, you should generate the hydrogen. Okay. And you can convert that hydrogen into ammonia and you can store that ammonia. And when you require the hydrogen again, just convert ammonia into hydrogen. Okay. So it is also kind of storage for the energy. Okay. So you can store the surplus generated hydrogen through the electrolysis into a form of ammonia. Okay. And what is the other use of ammonia?
Fertilizer.
Yes. So in fertilizer industry also ammonia is majorly used. Okay. So to have a green economy and to reduce the carbon footprint, we need to have green ammonia. So the green ammonia is also supplied to the fertilizer industries. Okay, so that they can use some part of green ammonia and they can reduce their carbon emissions. So the correct answer is metal hydride. So metal hydride is a chemical storage. Now there are some requirements for materials for hydrogen storage. Okay, so because if you are using material for the hydrogen storage, then like in metal hydride, so then there should be high hydrogen capacity per unit mass and unit volume so that you can store more hydrogen. It should operate at moderate operational temperature and pressure. The heat of formation should be moderate. It should have reversibility. The kinetics should be faster. It should have high stability against oxygen and moisture. It should have long cycle life, low cost and high safety. So these are the important parameters your material should have, which will be used for the hydrogen storage. Now in terms of hydrogen storage, we can store either in the adsorption or by the absorption. So what is the difference between the adsorption and absorption?
Adsorption is just a surface level property where you have the hydrogen at molecules adhering to the surface of that metal, whereas absorption is they form bonds. It breaks into single atoms and they penetrate into the uh, deep within the surface, and they form bonds with they settle in the inter molecular spaces of the metal, post metal.
Nice. So we can say the adsorption is surface phenomena and the absorption is bulk phenomena. So you can see here, this is hydrogen, okay, molecule. So it's directly attaching over the surface of the material. Okay, so it's adsorption. And here you can see the hydrogen. It converting into the hydrogen atoms, H atoms, and it's diffused inside the material and also forming some kind of weak bonds. Okay, and it's inside the material. Okay, so it's absorption. Which assumption is taken in BET adsorption isotherm theory? There is a BET adsorption isotherm theory. So which assumption is taken there? A, gas molecules are physically adsorbed in monolayer. Gas molecules are chemically absorbed in infinite layers being interacting each other. Then C, layers being non-interacting. And the D, gas molecules are chemically adsorbed in monolayer.
C.
Okay. So let's see. So the answer is C. The gas molecules are physically adsorbed in infinite layer being non-interacting. So this BET is widely used test. Anybody have you done BET? So you can do BET analysis in which you can find the what can you find in BET? The surface area. Okay. So the BET is these are the name short form of names Stephen Brunner, Paul Emmett, and Edward Taylor. So BET. Okay. So they considered an assumption gas molecules are physically adsorbed in infinite layers. Layers are non-interacting. So the also Langmuir model is valid for each independent layer. Okay. I'm also not expert of these isotherms, so I suggest refer to a reference book. You can refer this book to understand deeply about these. Now, zeolites are classified on the basis of which ratio? Silica, aluminium, silica, oxygen, sodium, alumina, silica, alumina.
Silica, alumina. Option D.
So we have one answer, option D, silica, alumina. So have you gone through the class videos?
Yes.
Yes, yes.
Yeah. Okay. So those who have gone through the class videos, they are giving correct answers. So I suggest again, please go through the class video before the live session. So the correct answer is D, silica, alumina. So zeolites are a family of highly crystalline aluminosilicate materials. So 3D crystalline aluminosilicate built up of TO4. So zeolites are crystalline solid structure made of silicon, aluminum and oxygen that form a framework with cavities and channel inside where cations, water and or small molecules may reside. They are often also referred to as molecular sieves. So important, they are referred as a molecular sieves. Zeolites are classified on the basis of silica alumina ratio. So zeolites with low silica alumina ratio 1.0 to 1.5. Zeolite with intermediate silica alumina ratio 2 to 5 and with high silica alumina ratio 10 to several thousands. Okay. Have you heard zeolite earlier as a molecular sieve? It's widely used in a purification system.
PSA tower we are using in.
Yes, yes. So Hitesh, are you using in your company the PSA?
Actually, we are using for the nitrogen generation actually.
Okay. So nitrogen generation, basically you are having the air separation unit then.
Actually, yes, yes.
Okay.
PS means PSA tower inside there is a some sleeves there. That material is not zeolite, maybe some carbon type material.
Okay. Yeah. So PSA is widely used in PSAs. Sorry, zeolite is widely used in PSAs. So as you have seen here, it's make a framework with cavities and channels inside. So it will only pass through this from these cavities and channels only. The material which can pass, that will pass, otherwise other materials will be trapped. Okay. So this sodalite, NaX, ZSM5, NAA. So these are the some zeolites. TiFe can be classified into which category of hydride? Complex.
What does mean weight percentage?
So weight percent is like you are having, if suppose I am saying 1.1 weight percent. So like you are having a base material and you are adding some other material into that. So the addition of the other material will be 1.1. So basically the total weight, suppose its total weight is 100 gram. Then 1.1 gram is the material that you have added. So
Okay. Okay.
1.1% is the new material that you have added into that.
Okay.
Okay. So as you have seen that it is this complex is the crystalline solid structure made of silicon, aluminum, and oxygen. So you are changing this silica to aluminum ratio. Okay. So based on this ratio, the overall weight percent will change. TIF, TIFE can be classified into which category of hydride? Complex, metal, covalent, or ionic?
Is it ionic? Right? D, option D.
If you have an answer, option D. Anybody else think about it? Okay, so the correct answer is B, metal hydride. So TIFE is a metal hydride. Okay. Now, so storage, so physical or material based, physical, compress, liquid, and cryo. In material based, the dissociative hydrogen, sorry, dissociative storage, H2H, and molecular storage. So in this, it's chemical hydride, metal hydride, and molecular high surface material. So it will be, you can say, the adsorption based, and this will be what? So it is dissociative storage, H2H. What is the meaning of this? So here we have seen few slides back two phenomena, adsorption and absorption. So it's high surface material you require, so that only this is your material. So hydrogen molecule will attach over the surface, and in this it will dissociate in hydrogen atoms, and they will form some weak bonds with the material. So physical adsorption, surface phenomena, absorption, bulk phenomena, covalent bond is there here, van der Waals forces. Now comparison of different storage methods. So here volume of 4 kg of hydrogen compacted in different ways with size relative to the size of a car. So the size of these containers are relative to the size of the car. Okay. So it is hydrogen compressed at uh, I think 200 bar. Anybody, can you see it? It's just
Yes, it is 200 bar.
Yeah, 200 bar.
yeah, it's 200 bar. Then it's liquid. Then it is having La, Ni, and H. I don't see exactly the number. And this is
LaNi2H5.
H5. Okay, yeah, nice. And this is Mg2 NiH4. Yeah, okay. So basically, you can compare if you are compressing the hydrogen at 200 bar. Okay, So see, this much of volume is required. So see the size comparison with the car. So is it possible to put this much of cylinder in this car? Yes or no?
No.
No, actually, yes, it's possible. You can put this cylinder into the car, but it's not reliable actually. If you put this cylinder in the car, then where the passenger will sit? You can put this cylinder, no issue, but then the space will, there will be only like a driver or one person can sit along with the driver. So the whole back space will be occupied with the cylinder. So it's not good option to put this cylinder into the car. You can put it, but it's not advisable. And then the liquid, so still the size is very small. You can easily put, okay. But with the metal hydride, the size is further reducing. So just one thing, the size reduction between these three is not that much, okay, as compared to the size of these three with this, okay. So it's clear that we should not use the compression, okay. We should avoid it to save the space in our vehicle. So if the liquid hydrogen also, you can see here, it's also occupying almost similar space as compared to the metal hydrides. So what is the use of this metal hydride storage? What do you think?
I think it's cheaper than liquefying hydrogen.
Yes. So,
And also this liquid hydrogen, we have a issue of boil off also.
yeah. So due to the complexity, due to the liquefaction, due to the like chances of some kind of mishappening in case of uh, hydrogen liquid state, okay, so cryogenic issue, then possibility of heat loss and all. So there are so many issues. That's why we should use metal hydride, okay, because size reduction is not that much, but still size reduction is there. But the thing is that the complexity is reducing so much, okay. So the medium here you can see solid storage LaNi5H7. The energy density is 1944 kilojoule per kg. Liquid hydrogen density is 14900 kilojoule per kg. Gaseous hydrogen this much and gasoline this much. Okay, so you can compare. So here we can see that in solid storage, the energy density is not that much. Okay, 1944 with this material. That's why we are exploring some other materials also that can store more hydrogen. Okay. So this is a curve. It's representing the volumetric hydrogen density kg per meter cube and the gravimetric density mass percent. Okay. So for different material, you can see. So it's liquid at 20.3 Kelvin. Then this is LiAlH4, LiBH4. Okay. And the classes of hydrides. So ionic hydrides, covalent polymeric hydrides, metallic hydrides, and metastable hydrides. So the ionic hydride, hydrogen is negatively charged ion. High conductivity is found by alkali and alkaline earth metals. Example NaH, CH2, LiAlH4 and NaLH4. So Li plus H2 973 Kelvin LiH. Covalent hydride found with non-metals, weak van der Waals forces, NH3, H2O, H2S are example. Metallic hydride found with transition metals, rare earth metal, and lanthanide as metallic bond. So ease of uptake and release, good storage capacity. AH2, FeH2, and VH2. Some examples. Okay. What is uptake and release?
The
Means
amount of
absorbed and absorbed.
hydrogen adsorbed or absorbed. Absorbed, sorry, here. In this case.
Yeah. So because if we are having a particular like volume of a cylinder in which we have filled metal hydride, so we are storing hydrogen into that particular cylinder, a particular amount of hydrogen. So we can use that amount. After that, we need to refill that. So the ease of uptake and release. Okay. So metal hydrides, so they combine with hydrogen directly, high hydrogen storage capacity on volume basis, simple method of uptake, store for any duration at ordinary temperature and pressure, quite stable below their dissociation temperature, safe to handle and store hydrogen. Tank design don't require to sustain high pressure or low temperature. Okay. So this is the benefit. A tank design don't require sustain high pressure or low temperature. Safe to handle and store hydrogen. Now the mechanism. So this is H2 molecule. Okay, this is your metal surface. So the H2 molecule approaching the metal surface. So you can see the molecules are approaching. Interaction of H2 molecule by van der Waals forces. So they have attached our surface. Then chemi-absorbed hydrogen after dissociation. So now it's dissociated into two atoms. Occupation of surface sites and diffusion into the bulk lattice sites. So further, they diffused into the lattice, bulk lattice sites. This is the mechanism of metal hydride. So there is a metal plus 0.5x H2 MHX plus heat. So what is the meaning of this reaction?
It's exothermic.
So the heat will be released. Okay. Now suppose I have stored the hydrogen in a metal hydride. Then how will I release that hydrogen?
You will have to heat the metal hydride.
Okay. So what is the complexity in this metal hydride storage system? What do you think?
So it is supply of heat during the release of hydrogen.
Yeah. So basically you can say that thermal management is very important in metal hydride storage because heat is releasing, and again to release hydrogen you need to supply heat. Okay, so thermal management of your storage is very important in this case. So the absorption, when supply pressure is higher than the equilibrium pressure, it is exothermic process. Equilibrium pressure is temperature dependent. In desorption, when equilibrium pressure is higher than the outlet pressure, it is an endothermic process. Equilibrium pressure is the temperature dependent. Okay, so in this process heat is evolving. Here you need to supply the heat. So under low temperature or high pressure, the hydrogen atoms can enter the gaps in the parent metal, forming a solid solution. Changing pressure and temperature will cause the hydrogen to either be adsorbed or resorbed. Okay. So what is the value of degree of freedom in alpha plus beta region of PCT isotherm?
It's a 1. Option D.
Okay. Anybody?
D1.
Okay.
One.
What is your
Yeah,
reasoning?
from the curve it is showing F equal to 1.
Okay. So it's showing F equal to 1. So using the Gibbs free rule, C plus 2 minus P. What is C and what is P?
P is the actually phase and C actually I don't remember actually, but the it also P is actually phase. Means
Okay.
alpha beta plus hydrogen phase.
Okay. C is the components. Okay. And P is the phase. So here you can see alpha beta. So phase 3, component 2, put the value F equal to 1. So the correct answer is D, 1. So what is the meant by boil off loss of hydrogen? Option A, evaporation of hydrogen due to conversion of ortho to para hydrogen by means of reducing temperature. Evaporation of hydrogen due to conversion of para to ortho by means of reducing temperature. Diffusion of hydrogen atom into metal lattice. Condensation of hydrogen due to conversion of para to ortho hydrogen by means of reducing temperature.
A.
B. Sorry, A.
Okay. So do you want to explain?
Sorry, you asked us to explain?
Yeah. Earlier you were saying B then A.
No. Actually, I just mistook ortho to para only. Higher energy
Okay.
to
Okay.
lower energy. So when the energy
Mhm.
is released, that energy is absorbed by again the liquid hydrogen and boils off. That is what is the boil off loss. Yeah.
Yeah. Okay, so in the ortho to para conversion, it's ectothermic process. Okay, and due to this, some liquid hydrogen can boil off and evaporation of hydrogen can be there. So this is called boil off loss. The correct answer is A. Arrange the various phenomena involved in hydrogen absorption process in chronological order. Nucleation and growth, formation of hydride phase, chemisorption and dissociation, penetration into metal surface, diffusion, physioabsorption.
Already their answer B.
Okay, answer is already mentioned. Okay. Anybody remember this? That's important.
Yes, sir. Yeah. So you want us to explain why it is the chronology?
So professor covered this in the class, and I think it's important for your exam also. So the absorption, these are the steps and the order A to F. So physioabsorption, then chemisorption, then penetration of the metal surface, then formation of hydride phase, then diffusion, then nucleation and growth of the hydride phase. So A, B, C, then D, then E, then F. Okay, it's important. The correct answer is B.
Actually, here one doubt is there.
Mhm.
Actually, this phase alpha is after the step F actually, and the phase beta is
Mhm.
outside. But as per the PCT diagram, the first it will come the alpha and then alpha plus beta like that. So can you little bit explain this?
Okay. Okay, so actually I have to go through these. So this topic is also new to me. Yeah, maybe in next class we can discuss it.
Sir, this one, if you, I can just give a little clarity on this.
Yeah,
This
please.
this one is actually the step is the last step, where it nucleates and grows. So when this is only in the fourth, that last step, when the nucleation happens, initially when the concentration of hydrogen is less than that of the metal hydrate, that is called the alpha. So when the concentration of hydrogen, when the diffusion keeps on happening and hydrogen atoms accumulate, I believe so, and then the concentration of hydrogen increases. That is when you get
Okay.
alpha plus beta. And when the concentration is high, that is when the beta is there. That's what. So in this particular question, what we just now discussed, the formation of hydride phase, sorry, 1 minute, nucleation, nucleation. The first one, nucleation and growth, that one is only defined in that graph.
Okay. So I'm not sure. Maybe you can refer to this discussion, or it's better to refer a reference book for more clarity on this. I'm not sure about this. I'm totally unaware of how this phase diagram is happening and all. Okay, maybe we can discuss in next class in more clarity about this. I will try to rebrush my concept. Okay, let's move further. So the crystal structures, so it's alpha, then beta, and then gamma. So beta half-filled tetrahedral sites, the gamma is fully filled void leads to distortion. And hydrogen goes into the tetrahedral and octahedral voids of BCC, HCP, FCC type lattice. Formation of hydrides lead to the expansion of the lattice, which leads to reduction in the symmetry. The stability of hydrides depends on the size of the interstick. In BCC lattice, the tetrahedral and octahedral void distort largely. In FCC lattice, hydrogen concentration in the octahedral is low. So maybe this can become a question in your exam or all. So it's important to remember this. So in BCC lattice, the tetrahedral and octahedral void distort largely. In FCC lattice, hydrogen concentration in the octahedral is low. For the measurement techniques, so for the measurement, there are volumetric technique, gravimetric, and temperature programmed desorption. Okay. So in the volumetric technique, you have like a system in which you can use standard cells and vacuum and atmosphere and the hydrogen gas you can. So you basically uh, you can use a particular gas to see the adsorption. The exact formula for this was covered in the class, so go through the class notes. Okay. In the gravimetric, you have a microbalance chamber in which you can measure the weight. By this, like the weight before the adsorption, weight after the adsorption, the difference. So in that way, you can have a measurement of the adsorption. So in summary, metal hydrides can reversibly store hydrogen. What does it mean reversibly store hydrogen?
That means when you recover the hydrogen from the metal hydrides, you can completely have the metal hydride in its original form.
Yeah, nice, right. So high storage capacity on volume basis, absorption of hydrogen to form metal hydrides in a multi-step process, different ways to measure the uptake of hydrogen. NPCT curves are used to study the behavior of hydrogen absorption and desorption. What is the specific energy consumption in kilowatt hour per kg of hydrogen liquefaction in ideal Lind-Hampson cycle and dual P Claude cycle respectively? It's the direct question. If you have gone through the class notes, then only you can know the answer. The answer is B. 16.24 for ideal Lind-Hampson cycle and 6.66 for dual P Claude cycle respectively. So if you want to have large scale liquefaction, then these are the process which we can follow. So simple Claude, Capitja, we have covered this already. Like it is using reciprocating engines, dual P Claude, pre-cooled Lind-Hampson, pre-cooled dual P Lind-Hampson, helium pre-cooled Claude, and pre-cooled mixed refrigerant and cascaded cycles. So in simple Claude cycle, you can see you have a cooled compressor, then you have heat exchangers to further reduce the temperature. So then you have a throttle valve. So the purpose of these heat exchanger to reduce the temperature so that in the throttling we can have cooling. Okay. So in between we also have expander. The expansion valve device is used to reduce the temperature before throttling. So then we can have liquid hydrogen. So this is a simple Claude cycle. So you can do the mass and energy balance. So if you consider these points like 1, 2, 3, E, 4, 5, 6 and all. So you can do the mass balance, energy balance, Okay, from the energy balance, if you put these values, then you can have this equation. So here the small w is the net energy consumption of cycle. The capital W is the net power consumption. Sx is specific entropy of stream. The specific energy consumption is energy consumption per unit of mass liquefied, kilojoule per kg. So energy required or consumed per unit mass of liquefied hydrogen. Okay. So this will be the case. The COP, the cooling provided by the working fluid to net input power of cycle, coefficient of performance, COP. Yeah, so Kapitza process, use of reciprocating expansion engine. We have covered this slide previously. So in pre-cooled Linde-Hampson cycle, so we have a compression with intercooler. Then you can see there here we are using the liquid nitrogen cooling. In the Claude cycle, we are using an expander, but in the Linde-Hampson cycle, pre-cooled we are using a liquid nitrogen cooling. Then the isentropic expansion, then liquid hydrogen. Okay, suppose if there is some boil off or some losses, then that is supplied back to the initial point. So specific energy consumption of idle L cycle is 16.24 kilowatt hour per kg. For Claude, it is 22.1 kilowatt hour per kg. Performance can be improved by throttling over two pressure levels. Energy requirement can be reduced pre-cooling and dual pressure. So SEC of specific energy consumption of ideal dual pressure LS cycle is 12.12 kilowatt hour per kg, and for dual peak load 6.66 kilowatt hour per kg. So see the question was about to the specific energy consumption SEC for ideal Linde-Hampson cycle and dual P load cycle. So 16.24 and 6.66. This is a different process, Collins process. In this, you have multiple heat exchangers with two expander. Okay. So it's a kind of a cask. So other system, we have also other systems in which we can have helium pre-cooled. So like in previous, we have seen the nitrogen pre-cooled nitrogen cooling, liquid nitrogen cooling. We can also have helium pre-cooled. We can have Joule-Breton pre-cooled cycle, mixed refrigerant pre-cooled system, or cascade systems. So if we use the helium pre-cooled, then it can reduce the compressor size and helium act as the working fluid. Joule-Breton pre-cooled, so helium act as a refrigerant in this. The final expansion is through the expansion engine and working fluid not liquefied. So this also use the expansion engine for the final expansion. Then the mixed refrigerant pre-cooled, the mixture of gases and vapor as working fluid in refrigeration, and the mixed refrigerant cycle act as a pre-cooler. In the cascade, independent cycle pre-cools other refrigerant cycles. Process closer to ideal reversible liquefaction. It is used for wide temperature required to improve liquid yield and efficiency. So in summary, several hydrogen liquefaction plants in world: USA, Japan, Canada, Holland, France, China, Germany, India, etc. The SEC for some plants is like for Praxair is 12.5 to 15 kilowatt hour per kg. Ingolstadt 13 to 15 kilowatt hour per kg. And the target of US Department of Energy is 6 kilowatt hour per kg for large plant. Reduction in energy possible by process integration and other improvements, but it's complicated. Capital cost is 40 to 50% of total liquefaction cost. So they are very costly to install. Very large plants modeled and developed 50 ton per day with liquid helium cooling and 4 ortho to para converters. They have 8.73 kilowatt hour per kg of SEC. Pre-cool, flowed and JB 5.85 kilowatt hour per kg and 4 JB cascade and mixed refrigerant 5.35 kilowatt hour per kg. So this slide is showing the current status of this technology. Okay, simple question, we have covered it already. Ortho to para conversion of hydrogen is endothermic, exothermic, thermoneutral, very fast reaction.
Exothermic.
Yeah, we have covered it. It's exothermic. It will release heat. The Joule-Thomson coefficient of hydrogen at ambient temperature is negative, positive, 0, infinite.
Negative.
Yeah, it's negative. That's why at room temperature, if you do the expansion, then there will be heating instead of cooling. At NTP, what is the percentage ratio of ortho to para isomer in the normal hydrogen?
75-25.
Yes, 75 and 25. Which tank geometry in general have lower surface to volume ratio in terms of liquid hydrogen storage? Sphere, cylindrical, cuboidal, conical.
Sphere.
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 Yeah, nice. So the sphere is the right answer. It's a geometry which have lower surface to volume ratio in terms of liquid hydrogen storage. Which of the following factor does not contribute towards boil-off losses in liquid hydrogen storage? Ortho to para conversion, thermal stratification, sloshing, and para to ortho conversion.
Para to ortho.
Para to ortho.
Why?
Because
I
it
think
is
ortho,
higher, it's endothermic and it's higher, it needs higher energy. Ortho is higher energy than para.
Right. Okay, the correct answer is para to ortho. What is meant by the dormancy? Time taken for onset of evaporation of hydrogen, time taken for complete evaporation of hydrogen, time required for
First,
discharging liquid hydrogen from one vessel to another vessel, and time taken in liquefying hydrogen.
time taken for onset for the position of S2.
Yes. So it is time taken for onset of evaporation of hydrogen is called dormancy. Which among the following is zeolite? Carbon nanotube, ZSM5, EIFE, ZIF100.
ZSM5.
Yes.
It's
The
also
answer is
used for FCC.
ZSM5.
Yeah, it's also used for FCCU, catalytic cracking
Okay.
for gasoline production. Yeah.
Okay. So yes, it's ZSM5. On the hydride formed by reacting with alkali or alkali earth metals can be classified as covalent metal, ionic, high entropy, alloy based hydride.
Iconic hydride. Ionic.
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 Okay. The answer is ionic hydride. So it's formed by the alkali and alkaline earth metals. Now select the correct relation for absorption of hydrogen in metal hydride. PS supply pressure, P equilibrium pressure, and PA ambient pressure.
Option A, supply pressure is greater than equilibrium pressure.
Supply
Yes.
pressure is
Correct answer is option A. So we have seen that the supply pressure is higher than the equilibrium pressure, then the absorption happens, and when the equilibrium pressure is the higher than the outlet pressure, then the desorption happens. So this one is exothermic. Equilibrium pressure is temperature dependent. Okay, so heat will be released. In this, you have to provide the heat. Arrange the various phenomena involved in hydrogen absorption process in chronological order. So we have covered this already. Okay. A, B, C, D, E, F. So now let's go through some slides that was covered in the class. So questions are already covered for today's class, because in each class we have target of 20 questions. So we have covered 20 questions today. So now, but we have left some time. Let's go through some slides. So designing optimized adsorbent. So if we want to use an adsorbent, then we need to optimize the design so that we can have the maximum adsorption of the hydrogen. So the increasing adsorption sites per unit weight and volume. Okay. So we need to increase this absorption sites per unit weight and high volume. So we need to have high surface area and high pore volume. Increasing the heat of adsorption. So we need to reduce the hydrogen spillover. We need to have narrow pore. Okay. And we need to have unsaturated adsorption sites. The types and shapes of carbon material, like granular type, pellet, and powder. Okay. So surface area of activated carbon is around 800 to 1700 meters square per gram. And for AX21 it is 3000 meters square per gram. So here you can see if we have carbon allotropes, so we can have 0 dimension, 1 dimension, 2D and 3D carbon allotropes. So in 0 dimension you can have diamond, graphene dot, carbon dot, onion like carbon, fullerene. So in 1D you can have carbon nanotubes, carbon nanohorns, and multi-volt carbon nanotubes, single-volt carbon nanotubes. In 2D, graphene, multi-layered graphene sheets. In 3D, graphite and diamond. So these are the different allotropes for carbon. So carbon is also used as an adsorbent for hydrogen storage. So carbon is well known as one of the better adsorbent for gases. A range of carbon nanostructures are carbon allotropes like activated carbon, CNT, carbon nanotubes, activated carbon fibers, ACFs, carbon nanofibers, and carbon nanohorns, graphite and graphene, etc. are commercially available. So carbon materials possess high hydrogen storage capacity due to porous microstructure, micro and meso and macro, with high specific surface area, 10 to 3000 meters square per gram, and low mass density. Okay, so these are the forms. We have earlier also seen these forms. So this is about the carbon. I think one of you was telling that you are using the carbon for the adsorption, for the purification of nitrogen from air, right?
Yes, we are using.
Okay, so what kind of carbon you are using in your system?
Actually, I have seen this pellet type.
Pellet type. Okay, so you are using this pellet type of carbon in your system.
Yes.
Okay, so do you know the surface area? Specific surface area for your
No,
this
no, no,
pellet
no,
type
no.
system? Okay.
No. The all details that actually I don't know. Actually, I'm from the operation department, so I only know the what type is available. All
Okay.
details in detail I don't know.
Okay.
Surface area I can see in multi-wall, carbon nanotube and uh, carbon nano. You can carbon nano tube. We can see the more area, surface area.
Yeah. So geolites. Okay, we have seen this already. Metal organic frameworks, MOF. So metal organic frameworks are a class of compounds consisting of metal ions and or metal oxide clusters coordinated to organic ligands to form one, two, or three-dimensional structure. So what is the meaning of this 0 dimension, 1 dimension, 2 dimension, 3 dimension? Anybody?
And we might be understand like in mathematics, like three
Yeah.
dimension and two dimension. I don't
Yeah.
know
So
exactly.
yeah, just let me know. What do you think?
It does mean sometime have a length and weight, sometime a length and weight and depth, like that something.
Okay. Anybody else? What about 0 dimension? Because here we also have 0D.
No XYZ. Maybe in dot.
Yeah, right, correct. Dot. Anybody else?
I think it may be the related to the porosity means 3D we have inside the one material having porosity, one particle, and maybe the dot having we have to put so many dots, and among the so many dots we have some porosity like that.
So porosity is not connected to the dimension. So the uh, it's like one of you have already told that X, Y, and G. So okay, yeah, that's correct. But what is the meaning of that? So what those X's are representing?
Means surface area, maybe, or you can say some structure or definitely surface. XY make a surface, XYZ combined make a some volume.
Yeah, nice.
Active sites,
So
active sites, is it?
you can say, but the correct keyword you are missing actually.
Yeah.
You are you're like I can understand your emotions, but the correct keyword you are not.
Actually, I am not
Yeah,
background of
missing.
chemical
Yeah,
engineering. I am electrical.
yeah. So basically, the when we are talking about this 0D, 1D, 2D, and 3D. So basically, as we are increasing the dimension, so we are inserting one more spatial dimension to that. Okay, so that's the keyword, spatial dimension. So 0D when means no dimension at all. So basically, you are representing the system in a bulk or a dot. So you will consider only a dot. Maybe the system is quite big, complex, but you are not bothered about the dimension and all. You are considering, okay, I am considering my system as a bulk, as a dot. Okay, like this graphene dot. So you are considering only a dot in the zero dimension. So all the properties, all the system, you are maybe the variation, how the variation is changing. So you are not bothered about all the things. Just only this dot you will consider. Okay. So those who are from chemical engineering background, maybe they have used the ESPN. Anybody have you used the ESPN software? Anybody have used ESPN? ESPN Plus for the chemical system modeling flow sheet
Yeah,
program?
I've used it.
Yeah.
Yeah,
So you
Mehul here. I've used, yeah.
so you have used the ESPN. So you do, because in ESPN you have already inbuilt blocks. Okay. So
Yeah,
you can put them together, and you can give them mass and energy, and you can
yeah,
have the mass and energy balance. So what do you
yeah.
think? You are doing a modeling there. So what kind of modeling you are doing? Is it 0D? Is it 1D, 2D, or 3D?
I think it is 1D mostly because
Okay. Suppose let me. Okay, if you are using custom modeler, I don't know. Suppose you are having a
Aspen. No, I've
separator.
not used Aspen custom modeler is little tricky. I've not used that
Tricky.
yet.
Okay. Then
Yeah,
okay,
but
if you're
it's
not
used for
using the
reactor modeling. Yeah, yeah.
reactor modeling, if you use reactor modeling, then what do you think? Is it 1D or 0D?
So, like, say, like there's a difference between this Aspen and this CFD. CFD is 3D. You can, they give spatial dimensions, all three spatial dimensions for heat transfer,
Yeah,
for transport to now. But I think mostly the simulation, what we use for heat and mass balance is mostly 1D.
it's 0D actually.
Okay.
Yeah,
Okay. Okay.
so yeah, it's 0D. You don't consider the spatial dimension. Maybe
Right.
the
Right.
maybe some model of can also considering the spatial dimension, this variation over length. Okay, then they can be considered as 1D. But suppose
I think
in the
variation, yeah, variation over length is there. Like, say, if you want to consider, temperature profile across a solid metal, that is available in some simulation
yeah,
software.
some simulation, yeah.
Yeah,
So those
Unisim
they are
design I
using the
use.
1D.
Yeah,
Yeah.
yeah, that is
So
1D. That's why I said 1D.
yeah. So every block is not a 1D, but some part of that component is 1D. But mostly the S1 is 0D. Okay, suppose if you are having a separator in that. So what is the separator doing? So you are giving a condition to separator that okay, there are one inlet, two outlets. The inlet is having nitrogen and oxygen. It's separating the nitrogen and oxygen into two streams. So what do you think? Is there your separator block is considering any special dimension? No. So what your separator block is doing? So that is a block. Okay, you are giving a input and there's two output. So input is air, nitrogen and oxygen. Output is two separate streams, nitrogen and oxygen. So what do you think? What is this separator? So it's a 0D. So we are not considering any variation how this the separation is actually happening. Okay. In real situation, you are having a reactor, so they are all three-dimension flow and everything is there. But in the ESPN modeling, we don't consider all the things. We are just doing the mass and energy balance. We are separating these two. So this is 0D. Maybe some reactor, if you are defining the kinetics and you are defining the profile and all, then maybe that is 1D. Okay. So each block is not 1D. Only some part of the block is 1D. Mostly it's 0D. In 2D, you are having two special dimension. Like you can vary the parameters over length and breadth. And in 3D, you can have variation in length, breadth, and height. Like you are saying in the CFD modeling. So if you are considering the heat exchange in all the three dimension, then you are doing the 3D. Okay, so this is the major difference. Uh, how many spatial dimension you are considering? That's is deciding the it's 0D, 1D, 2D, or 3D. Okay. Okay.
Okay.
So hydrogen storage capacities of different adsorption based materials. So here we have seen different materials, surface areas, storage, pressure, temperature. So we have like MOF 210, surface area is 6240 meters square per gram, and storage 176 milligram per gram total. Pressure 80 bar, temperature 77 Kelvin. Then MOF 177. So here we have given multiple examples of hydrogen storage and their capacities of different adsorption best materials. Okay.
So
So
best is MO,
hmm.
last slide. Best is MO 220 and NU 100.
So if you consider the storage, so the maximum storage if you see, so you are having is 176,
And
then
164
it's 164.
only.
But yeah, here we have given weight percentage. Okay.
Mm-hmm. But unit is different. How we differentiate with respect to different unit? Which one better?
So which one is better? So if I convert this into just a moment. So like this, you have given the weight now. So it's weight percent as I told you. Suppose it is 1 gram. Okay. So the 7.5% of 1 gram is the hydrogen in that. So here you have given mg per gram. So you can convert this mg into gram and then you can have the weight percent. Okay.
Think might be because of different dimension of the material. You already say, na, 0 dimension, 1 dimension
No,
might be
no,
that.
no, no. The storage is not connected to that actually. It just because it's only reported by some authors, so they have reported in this form. They have reported in this
Mm-hmm.
form.
Okay,
It's
okay,
nothing connected to the dimension and all. So
okay.
No, and it is very difficult to compare also because it is in
Correct.
different
That is
temperature
different.
and
That is
pressure.
yeah, yeah,
So we cannot say this is better or
yeah. So you can not comment on better or like that. So they have these are the like examples.
it will
Area is
depend on,
different,
yeah, it will
pressure is
depend on the
different.
purpose where we
Yeah,
are using and
just
what
data
temperature
sheet,
pressure
nothing
is
more.
in.
yeah, yeah. It's a data sheet. Yeah. Okay. So in summary, weak interaction of hydrogen molecules and adsorbent high storage capacity is possible only at low temperature. Advantage of this method of storage is rapid kinetics, complete reversibility, high cycle life, and low heat of adsorption, and correlation between hydrogen uptake or volume or pollution effect. So these are the recommendation book. Those who want to learn more about this adsorption and adsorption process, how the equilibrium is happening, about this alpha, beta, and all. So these are the books you can refer, some journals. Okay. So yeah, this is from my side. So, but still we have 15 minutes left. So then now I think we can have some general discussion. So how many of you are from chemical?
Yeah, I'm Mehul. I'm from Bangalore. I'm from chemical engineering background.
Actually, I was having some network issue. Please speak again.
Yeah, I'm Mehul. I'm from Bangalore, and I'm having background in chemical engineering. My basic is in chemical engineering.
Okay. Okay. And how many are, so one, anybody else is from chemical, mechanical? Okay. So,
Sir, I am from Mumbai and I have a background in engineering.
okay. Okay. So we are having like one or two from mechanical, one or two from chemical, and I think electrical.
Me only.
Okay. Deepak only. So what about this Mithun? Mithun?
The electronics,
Okay, electronics. Jayaprakash?
electronics and instrumentation.
Okay, so then okay, so we are having diverse audience. So let me ask you a very simple question. Okay, so suppose we are having two chairs. One is wooden chair and one is metal chair. Okay, so we are having two chairs. One is wooden and one is metal. Both chairs are outside in the ambient condition, and the ambient temperature it's not like like the NTP. Just consider that day is very hot actually. So we are having a heat wave on that particular day, and the temperature is around 50 degrees centigrade. Okay, and your colleague asked you to sit on one of the chair. One is wooden and one is the metal.
Wooden.
So what do you prefer? On which chair you will sit?
Definitely wooden.
Definitely.
Okay. Anybody else? So what is your name?
Deepak.
So
Good
Deepak
answer.
will sit on the wooden chair. Anybody else? So Deepak, tell me
Obviously
why will
wooden.
you sit? Okay, so we have another person also. He will also sit on the wooden chair. So mostly everyone will sit on the wooden chair. So now just tell me one thing. Why not on the metal chair?
Because metal is a good conductor of heat, it will absorb heat and get heated up. So if you sit on it, you will get the heat sense of heat.
Okay, okay, nice, nice. And Deepak,
Same,
what is
same,
your
same,
reason? Same reason.
same,
Okay,
same.
I think
okay,
the specific heat capacity of metal is lower, so it gets heated up faster.
okay, nice,
Heat
nice. So
heat
yeah,
coefficient material is very high, na? They absorb heat.
Very
yeah.
low actually. CP is very low for metals, so
Hmm.
they get heated up fast and they cool down also faster. But it's reverse for the like woods. I think wood and maybe yeah, water is also pretty high. So yeah.
Okay, nice, nice. Actually, good answer. So what about the temperature? What do you think? If I measure the temperature of both chair, which will be the hotter?
Of course, metal.
Metal.
Okay, metal will be the hotter. Anybody?
Of course,
Yeah,
metal,
metal should be water. Yeah.
and it will reach, I think, more than 50 degree because for the black body temperature on that.
Okay. So you mean to say it can go like more than 50 degree?
Yes.
Okay. No, just don't like go in that deep actually say black body and all, just normal. Suppose the maximum temperature is 50 degree, limited at 50 degree. We are not going into that deep actually. So just from thermodynamic point of view, we have like two chairs, one is wooden, one is metal, and the ambient conditions are there. So what is the temperature of like which chair will be the hotter chair? in terms of temperature? So actually you all have given the answer correctly, but now you all are confused again.
No, it is metal again.
Yes, it will be metal because due to the high conductivity, it will reach
Absorption of heat.
that equilibrium quickly.
Okay. So all are agree that the metal chair will be hotter. So let's just suppose, okay, the ambient is 50 degree and the chair are outside for like 4 hours. So I can say the metal chair is maybe around reach up to 47 degrees centigrade. Okay. And you mean to say the wooden will be the lower temperature. So it will be around 40 degree. Is it right? Just for example.
Yeah.
Just to see the difference. Okay. So there is 7 degree difference in metal and wooden. All are agree with this?
Maybe.
Since it is a long time, so temperature will be same in both because longer the time it will same. I think both will reach to the equilibrium. But if you
Yes.
say the heat content will be more in the metal because somebody said it is lesser conductive, lesser specific heat. But I said no, it is in the metal the specific heat content will be more. So total heat content in that mass of the metal chair will be more, but
Yeah.
temperature will be both same.
Yeah. This is the
N-
actually I want to
No,
know
I
actually.
will tell you
Yeah.
in metal chair because metal is conductive. So
Mm-hmm.
if you keep the chair is long time in heat or maybe high temperature, so all component or maybe metal will be spread out. Okay, but in a wooden chair, only heat will be surface because that is wood.
Good.
But
It is
what about
the
the temperature
conductivity
actually? I'm considering
conduct.
Mm.
okay, there is a sufficient time have given to both chair. So what do you think? What will be the like one of you have very well explained that both will be at equilibrium temperature. So that's a very key point I want to hear actually. So that's the correct answer. Both chair will be at same temperature. The only thing that you are feeling the wooden chair as a cooler at a lower temperature, but and the metal chair is like hotter. The only reason is the conductivity of the metal and the wood. Okay. Have you read the zeroth law of thermodynamics?
Yes.
I will tell you if both is same temperature, I will sit in wooden chair. After some time, I feel normal, but in
Yeah.
metal
What
chair,
is the
I will
yeah?
feel hot long time.
So that is the conductivity now because suppose
Correct.
this is the metal chair, okay? So the whole surface, the upper surface of wooden chair, and this is the metal chair, okay? So there's just consider we are considering layer, okay? So there are 10 layers, 10 such layers in metal chair and 10 such layers in wooden chair, okay? Just consider each layer. So now the conductivity comes into play. So metal, we know that it's very conductive, and wood, it's almost very less conductive. It's almost you can negligible as compared to metal. So what happens when you sit on the wooden chair, then your body will come into the contact with this upper layer. Okay. Then what will happen? There will be heat transfer from the wooden upper layer from the wooden chair to your body. Okay, you will feel that heat. But then what will happen? Because it's at high temperature, suppose 47 degree, then it will lose heat to your body. Okay, then it have to again gain the heat, but the conductivity is very low. So the lower layers will not transfer heat quickly to the upper layer. Okay, so that's why after just only 10 second or 20 second, the temperature of upper layer will not come to 47 degree instantly. It will take so much of time, and you are on this chair So it will not come to that point and you will feel cooler. But what happens in the metal chair? There are 10 layers, okay? Both are at equilibrium. So I'm considering 47 degree overall temperature, 47 degrees for this also. Okay, because as per zeroth law of thermodynamics, the embedded system, we have two bodies, so they will all be in the equilibrium. So when you sit on this chair, same, you will feel the heat transfer. So the upper layer will cool down. It will come to, you can say, 30 degree. But the conductivity is very high. So the bottom layer, just below this layer, directly transfer heat to this upper layer. And this layer again will be heated to near 47 degree. And you will again feel some heat over here. Then again so the heat transfer is very high. Heat transfer rate is very high. So you will feel continuously hot on this metal chair and cool on this wooden chair. So this is the difference. The conductivity is playing a very big role in this. Because what is the heat transfer? Heat transfer, we are just touching any object or anything so that we are having a direct contact with that. And we are feeling the difference of heat because your body is a different temperature and the surface is different temperature. So there is a heat transfer direct. So that is only the feeling. So the feeling is different, but the temperature will be the same for both case.
So that means
Anybody want
metal
to?
chair will cool down faster.
Yeah, but yeah, it will also cool down faster if you are having a, but you will feel hot on this chair for longer period than the wooden chair.
Yes, yes.
Yeah. The main point is that as per zeroth law, both are at same temperature. This is the main point actually. Like some of you were saying that, okay, the temperature will be different. No, because they are for a longer period, they will reach in equilibrium. So temperature is same. The only thing is your the sense of heat transfer due to the conductivity. Okay, anybody else want to say something about this?
Amit, not about this. This is Mehul. I had a
Yeah.
doubt in one of the assignment. I mean, the assignment questions on
Okay,
this
okay.
compressibility of isentropic hydrogen. There was a problem in week 7 assignment last question
Week 7.
10.
Okay, so
Yeah.
week
So
7, then you can email me actually. Yeah,
okay,
no
because
issue.
I feel I think what is missing is like the work required to compress hydrogen in isentropic case should also depend on the mass of hydrogen, right? Or the moles of hydrogen compressed, right? So this n term was kind of missing from that formula. So I'm not sure if because I calculated the work done and I think it turned out to be wrong.
Okay.
Uh,
Okay,
yeah.
no
So
issue. Actually, I'm not getting the whole picture of
yeah,
the
yeah.
question.
Okay. I'll tell
So
you that. Maybe I
yeah,
can email you. Give me
yeah,
your.
yeah. So my email ID have mentioned here on the last slide.
Yeah.
So just you can email me your query and I will try to respond as soon as possible.
Okay. I'll just take a snapshot of this.
Okay, so anybody can ask me any query. Please never ask query regarding the assignments. Those are due for submission. Okay, once your due date is over, then you
Yeah.
can ask it. Yeah.
Okay.
Okay. Okay,
So the
guys.
exam is going to be multiple choice questions or going to be lengthy answers.
I don't know about that actually. So
Okay.
mostly I think it will be MCQ and maybe like fill in the blanks type.
Okay. Okay. Okay.
Yeah. But you can ask the NPTEL team, just put an email to
Okay.
them and they will respond.
Right. And it's going to be a computer based test, right? I mean.
Yeah, I think so.
Okay. Okay.
Okay. Okay,
Thanks, Amit. Yeah.
guys. Yeah.
Okay, thank you.
Yeah.
Thank you.
Bye bye. Thank
Bye.
you.
Thank you. Bye.
Bye bye.